What if one day, astronomers pointed some of the most powerful telescopes on Earth toward the night sky and found something that didn't quite follow the rules of nature? This is the story of TR3 Atlas, an object first tracked by the Very Large Telescope, VLT, in Chile, one of the most advanced ground-based observatories on the planet. From the beginning, TR3 Atlas stood out. It wasn't just another faint dot among millions of stars. It showed unusual chemical signatures that sparked intense debate, even speculation that it could be something far beyond a natural body. The findings quickly spread. Some groups began suggesting that TR3 Atlas might not be natural at all, but instead an artificial structure, perhaps even the product of an alien civilization. The claim, while exciting, spread across forums, social media, and popular discussions much faster than the actual science. And yet, at the core of this debate is a simple question. What exactly is TR3 Atlas, and what makes it so unusual? To understand, we need to begin with the discovery itself. The VLT, based in the Atacama Desert, is a system of 4 giant telescopes, each equipped with instruments capable of detecting faint chemical fingerprints in the light from distant objects. Astronomers trained these instruments on TR3 Atlas and began to detect a number of emissions, gases venting from its surface, changes in brightness, and even the beginnings of a thin, hazy tail trace that pointed toward it behaving like a comet. That, in itself, wasn't strange. After all, comets shed gases and dust when they are warmed by a star. But what came next was different. When astronomers broke down the light with spectroscopy, a technique that separates light into its component wavelengths, revealing the chemical elements present, they noticed something unusual. The clear presence of nickel gas, but an apparent absence of iron. This immediately raised questions. Nickel and iron are cosmic companions. Both are created in the same processes, the catastrophic explosions of supernovae, the very furnaces where heavy elements are forged. In nature, they are rarely separated. Yet here, scientists were seeing nickel without detectable iron. The observation was striking enough that some voices outside the scientific community seized upon it, drawing comparisons to human industry. On Earth, refining metals like nickel often involves separating them from iron, a process carried out by technology, not nature. Could the same be true for TR3 Atlas? Was it possible, they asked, that this object had been engineered? But before we jump to conclusions, we need to be cautious. Science works by building explanations from data, not by rushing toward the most dramatic idea. And the reality is that, while the detection of nickel without iron is fascinating, it is not unprecedented. Still, TR3 Atlas became the center of speculation for one reason. It arrived with timing and data that seemed to challenge our understanding. Was it a comet behaving in an unusual way, or a window into something far more extraordinary? As we move forward, we will separate speculation from evidence. Because to understand TR3 Atlas, we must look at the history of such detections, the chemistry of these elements, and the broader lessons of how science interprets the unexpected. For now, we leave part 1 with the central mystery: nickel without iron in an object crossing our skies. Is it a comet or something stranger? When the data first came out, it didn't take long for speculation to spread far beyond the walls of observatories and scientific papers. On forums, in news headlines, and even in casual conversations online, people began asking, what if this is the first clear sign of alien technology? After all, a body venting nickel gas but not iron didn't sound like anything we usually see in the cosmos. To some, this was enough to jump to the conclusion that TR3 Atlas might be artificial. But this is where the story takes a turn. While the idea captured public imagination, the scientists who worked on the discovery never claimed that TR-3 Atlas was alien in origin. In fact, the published paper that reported the observation focused entirely on natural explanations. Yet the alien interpretation stuck because it appealed to something deep within us, the longing to find that we are not alone. We have been here before. In 2017, another object, Oumuamua, passed through our solar system. Its elongated shape, unusual trajectory, and lack of a visible tail sparked similar discussions. Could it have been a probe? A fragment of alien technology? To this day, debates linger. Some scientists, like Harvard's Avi Loeb, argued that we should at least consider the possibility. Others urged caution, pointing out how incomplete the data was. TR-3 Atlas now occupies a similar space in the public mind. It is a comet-like body, with features that invite speculation. But here lies the tension. Science is about measured evidence, while human curiosity often runs far ahead. So, what do we actually know about TR-3 Atlas? We know it has a growing tail of gas and dust behavior entirely consistent with a comet. We know it emits carbon dioxide in large amounts, again something we see in other comets. But then comes the nickel detection without iron, the detail that caught everyone's attention. Could this truly be an artifact of alien engineering, as some outside voices suggested? Or is it just another reminder that the chemistry of space is more complex than we imagine? Before we can answer that, we need to take a closer look at how observatories like the Very Large Telescope actually make these detections and why their data is both powerful and limited. If we want to understand what TR-3 Atlas really is, we first need to understand the tools used to study it. The Very Large Telescope, VLT, in Chile, is not just one telescope. It is a system of 4 massive optical telescopes, each with an 8.2-meter mirror. These instruments are perched high in the Atacama Desert, one of the driest places on Earth, chosen because its thin, clear air provides some of the best conditions for astronomy. Together, the VLTs can operate independently or combine their light to act as a single, enormous telescope. It is here, with specialized instruments designed for spectroscopy, that astronomers studied TR-3 Atlas. Spectroscopy is the science of splitting light into its component wavelengths. Every atom and molecule absorbs and emits light in unique patterns, like barcodes written in starlight. By analyzing these patterns, scientists can identify exactly what elements are present in a distant object, even if that object is so far away that it is only a faint speck of light in the sky. In the case of TR-3 Atlas, the VLT's instruments revealed 2 key things. First, there were emissions of carbon dioxide and a faint cometary tail, both signs that the object was warming as it approached the sun, releasing volatile materials into space. Second, and more controversially, was the strong signal of nickel gas without any detectable trace of iron. But the VLT was not working alone. Observatories around the world, and even space telescopes such as Hubble and the James Webb Space Telescope, are watching TR-3 Atlas as well. Each instrument brings a different advantage. Hubble with its sharp imaging from above Earth's atmosphere, Webb with its sensitivity to infrared light, and ground-based telescopes with their ability to repeatedly track objects over time. This network of observatories ensures that TR-3 Atlas is one of the most closely studied interstellar visitors to our solar system. But despite the immense power of these telescopes, their data still has limits. Light from TR-3 Atlas is faint, stretched thin by distance, and blurred by cosmic dust. The chemical signatures we detect are real, but the absence of iron in the data may not mean iron is absent in reality. It may simply mean that the signal is too weak to rise above the sensitivity threshold of the instruments at this stage. In other words, our telescopes are powerful, but they are not perfect. And when dealing with unusual detections, it is essential to keep this in mind. So while speculation grows outside of the scientific community, astronomers remain cautious. They know that the story of TR3 Atlas is not finished. As it journeys closer to the Sun, more gases will be released, and the chemical fingerprint may change. But even at this early stage, TR3 Atlas has given us something remarkable, a chance to see the universe surprise us, and to be reminded that nature often behaves in ways that challenge our expectations. Next, we will look more closely at the comet-like features of TR3 Atlas, and why, despite the controversy, most astronomers see in it the familiar behavior of an icy wanderer. When astronomers first turned their instruments toward TR3 Atlas, one of the strongest clues to its identity came not from speculation, but from something far more familiar: its behavior. As the object traveled through space, its surface began to release carbon dioxide in significant quantities. This release wasn't random. It was exactly the kind of volatile outgassing seen in comets' icy bodies that heat up as they approach a star, venting gases into space. Alongside this, astronomers saw the faint outline of a developing tail. At first, just a thin haze, it steadily grew as sunlight warmed the object. These two signs, CO2 emission and tail formation, are cornerstones of cometary activity. They suggest that TR3 Atlas is made, at least in part, of ices that sublimate when heated, just as countless other comets in our solar system do. In this sense, the object is behaving exactly as nature would predict. But if this sounds straightforward, the reality is more nuanced. TR3 Atlas does not match every expectation perfectly. For example, its carbon dioxide levels are unusually high compared to many well-studied comets. Its brightness, too, fluctuated in patterns that seemed unusual at first. These differences added fuel to the speculation. Could this be something other than a comet? Astronomers, however, know that comets are a diverse population. Some are rich in water ice, while others release mostly carbon monoxide or carbon dioxide. Even within our solar system, comets vary widely depending on where they formed and how long they have been exposed to the sunday. Seen from this perspective, TR3 Atlas may simply represent a different chemical fingerprint, an icy body forged in another planetary system carrying the unique chemistry of its birthplace. To the trained eye, its cometary tail is perhaps the strongest argument for a natural explanation. A true artificial object, a spacecraft or engineered probe, would not develop a tail of gas and dust in the same way. The presence of this tail makes TR3 Atlas look far more like an interstellar traveler cut from the same cloth as comets we already know, rather than a piece of alien technology. And yet, the mystery remains. A comet-like body with unusual chemistry is still unusual. For scientists, it is not enough to say, "It looks like a comet." They want to know why it behaves as it does, and what its chemical fingerprint reveals about the processes that shaped it. That brings us to the discovery that pushed TR3 Atlas into headlines: the clear detection of nickel without any measurable iron. Spectroscopy, the science of decoding light, is often subtle. A faint absorption line here, a tiny emission feature there, and suddenly an entire chemical story is revealed. In the case of TR3 Atlas, that story took a surprising turn. When astronomers studied its spectrum, they saw clear, unambiguous signs of nickel gas. In itself, this was not entirely shocking. Nickel has been detected in comets before. What was unusual was what they didn't see: iron. Nickel and iron are cosmic siblings, born in the fiery cores of massive stars and scattered into the universe during supernova explosions. These two metals are almost always found together. They form alloys, bind into the same types of minerals, and appear in similar proportions throughout the cosmos. So to find nickel in the gas phase without any detectable trace of iron, was puzzling. This was not how comets usually looked, at least based on what we had observed so far. For some, this immediately triggered bold speculation. Could the separation of nickel from iron be the result of an industrial process? On Earth, refining nickel often means separating it from iron. The very act of seeing nickel alone called to mind human technology, smelting, processing, manufacturing. Was it possible then that TR3 Atlas was not a natural object, but something engineered? It was a tantalizing thought. After all, if you were to design a probe, a spacecraft, or some other kind of machine, you might expect its materials to differ from those naturally produced in stars. To some voices outside the scientific community, this was exactly the kind of clue that pointed toward the artificial. But astronomers, cautious by training, knew better than to leap to such conclusions. The absence of iron in the data could mean many things, and an alien spacecraft was the least likely explanation. Before considering the extraordinary, they needed to carefully investigate the ordinary. Still, the signal was clear. Nickel was there, iron was not. The puzzle could not be ignored. This was the observation that gave TR3 Atlas its reputation as one of the strangest interstellar visitors ever detected. It was no longer just another comet candidate. It had become an object that challenged assumptions about the chemistry of small bodies drifting through space. The question now was simple, but profound. If not artificial, then what natural processes could explain nickel without iron? To answer this, we need to step back and look at the cosmic origins of these two elements, and why, under normal circumstances, they are nearly inseparable. To understand why the detection of nickel without iron in TR3 Atlas caused such surprise, we need to trace these elements back to their origins. Both iron and nickel are children of the stars. In the heart of massive stars, nuclear fusion builds heavier and heavier elements. Near the end of a star's life, fusion produces iron and nickel in abundance. When the star eventually dies in a supernova explosion, these elements are hurled into space, seeding the next generation of planets, asteroids, and comets. Because they share the same birthplace and are ejected together, iron and nickel are usually inseparable companions in the cosmos. In meteorites that fall to Earth, they are often found alloyed together, forming metallic crystals of iron-nickel. In planetary cores, like Earth's, both are present in significant proportions. Even in comets, which are icy relics from the earliest days of planetary formation, traces of both elements are normally detected. That is why astronomers expected TR3 Atlas to show signals of both. To see nickel clearly, while iron appeared absent, was like finding one twin without the other. In nature, such separation is rare. On Earth, the processes that separate nickel from iron are technological. We refine metals, we concentrate ores, we isolate nickel for use in alloys, batteries, and industrial machinery. For this reason, some outside observers drew a quick and dramatic conclusion. Nickel without iron must mean technology. But science does not work by analogy alone. Just because humans refine nickel artificially does not mean nature is incapable of producing the same outcome through chemistry and physics. The cosmos is full of processes that seem counterintuitive at first, but which follow natural rules once understood. For scientists, then, the mystery of TR3 Atlas was not evidence of alien engineering, but a challenge to explain how cosmic chemistry might lead to this imbalance. Could nickel exist in a form that made it more volatile, more likely to evaporate into space? Could iron be present, but locked into minerals too stable to release easily? These questions became the focus of research. The observation was real. The task now was to uncover a natural explanation that fit the data. And to do that, astronomers began comparing TR-3 Atlas to other objects where nickel had been detected before, and in the process discovered that this mystery was not entirely unique. The moment the discovery was published, one interpretation spread faster than any other. Nickel without iron means industry. On Earth, separating nickel from iron is rarely a natural process. The two elements are often bound together in ores like pentlandite, which miners extract and refine. In modern industry, nickel is prized for its resistance to corrosion and its use in stainless steel, batteries, and aerospace alloys. But to obtain it in pure form, humans rely on smelting, chemical extraction, and controlled processing, all hallmarks of technology. So, when astronomers reported the detection of gaseous nickel without any sign of iron in TR-3 Atlas, it was easy for some to jump to the conclusion that this resembled human industry on a cosmic scale. To those looking for evidence of extraterrestrial technology, it sounded almost too perfect, a material signature that echoed what we ourselves create. But science demands caution. Similarities to human processes do not automatically mean the same cause exists in nature. As Carl Sagan once warned, extraordinary claims require extraordinary evidence. And in this case, the evidence was far from conclusive. Yes, the spectrum showed nickel. Yes, iron was not detected. But absence of evidence is not the same as evidence of absence. The iron might simply be there in lower amounts, hidden below the detection threshold of current instruments. Or it might be bound in minerals that do not release gas easily at the temperatures Atlas had experienced so far. The alien hypothesis, while fascinating, rests on a weak foundation. Analogy. Because we separate nickel from iron artificially, some assume nature cannot. But the universe is vast, and its chemistry is complex. Processes we do not fully understand may create the same separation without any intelligent hand at work. Still, the idea of an engineered object was irresistible to many. Popular science outlets ran headlines hinting at alien technology. Online discussions flared. For a public eager to find evidence of life beyond Earth, TR-3 Atlas seemed like a gift. But astronomers, grounded in data, looked elsewhere for explanations. And when they began comparing Atlas with other well-studied comets, they realized that this was not the first time nickel had appeared without strong iron signals. In fact, the same had already been seen in interstellar comet Borisov and in Halley's comet, two objects whose natural status is beyond question. And this comparison would begin to shift the conversation from alien speculation back toward natural chemistry. While speculation about alien engineering captured headlines, the scientists closest to the data focused on a different path. Comparison. Science thrives on precedent. When faced with a surprising observation, the first step is to ask, has this happened before? If so, under what circumstances? And what explanations were found then? In the case of TR-3 Atlas, astronomers remembered that this was not the first time nickel had been detected in the gas phase of a comet. A few years earlier, the same had been seen in another visitor from beyond our solar system, 2I, Borisov. Borisov was discovered in 2019, the second known interstellar object after Oumuamua. Unlike its predecessor, Borisov showed a clear cometary tail and behavior that left little doubt about its natural origin. Yet when studied, its spectrum revealed the same puzzle. Nickel gas present, iron faint or nearly absent. Nor was Borisov alone. When astronomers looked back at data from Halley's comet, Earth's most famous periodic visitor, they found a similar imbalance. Again, nickel was abundant, while iron appeared only weakly in the measurements. These parallels were important. If two well-established comets, one interstellar, one from within our solar system, showed the same chemical quirk, then TR3 Atlas was likely following the same natural pattern. This realization didn't make the finding less interesting. On the contrary, it made it more significant. It suggested that cometary chemistry might include processes we had underestimated, processes that allow nickel to escape into gas form more easily than iron, regardless of whether the comet was native or interstellar. So instead of proving artificiality, TR3 Atlas was reinforcing a broader lesson. Our understanding of comet chemistry was incomplete. The story was no longer about whether Atlas was a spacecraft. It was about how nickel and iron, two cosmic siblings, could behave so differently in icy bodies wandering through space. And to explain that, astronomers turned to chemistry, the subtle differences between these two metals, and why one might appear in the gas phase while the other remained hidden. In 2019, astronomers were stunned by the discovery of 2I, Borisov, the first clearly cometary object to enter our solar system from interstellar space. Unlike the elongated and puzzling Oumuamua, Borisov behaved exactly like a comet should. It had a bright coma, a long dust tail, and volatile gases boiling off its icy surface as it approached the sunday. But when scientists analyzed Borisov with the same spectroscopic techniques now being used on TR3 Atlas, they found something remarkable. Its spectrum showed gaseous nickel. At first, this was surprising, because nickel was not expected to be abundant in cometary gases. More importantly, the corresponding signal of iron was either faint or nearly absent. This was the same chemical imbalance later seen in TR3 Atlas. But in Borisov's case, the explanation could not possibly involve technology. Borisov was unquestionably a natural comet. Its structure, its tail, its orbit, all fit the known physics of icy bodies. No one argued that it was an alien probe. So how was Borisov releasing nickel gas without a matching amount of iron? The best explanation came from the chemistry of these metals. Nickel is capable of forming volatile compounds that can break apart under sunlight, releasing nickel atoms into space. Iron, in contrast, is usually locked into more stable minerals that do not evaporate as easily. This meant that Borisov's nickel could escape into the gas phase, while iron remained bound within dust grains, invisible to current instruments. The detection on Borisov was a turning point. It showed that nickel in cometary gas was not a unique anomaly. It was a repeatable pattern, one that could happen naturally under the right conditions. This discovery also revealed something else. Interstellar comets carry with them chemical fingerprints from their home systems. Borisov's unusual composition hinted that the building blocks of planets beyond our solar system may not match our own perfectly. Each new detection teaches us not only about the comet itself, but also about the environment where it was born. With Borisov as precedent, TR3 Atlas suddenly looked less like an outlier and more like part of a growing pattern, a reminder that our expectations, shaped by the solar system, may not apply universally. But Borisov wasn't the only comet with this curious signature. Decades earlier, the same chemical imbalance had been detected in a much more famous visitor, Halley's Comet. If Borisov proved that nickel could appear without strong iron signals in an interstellar visitor, then Halley's Comet showed that the same could happen in our own cosmic backyard. Halley's Comet is perhaps the most famous comet in history, recorded by astronomers and chroniclers for more than 2,000 years. It returns to Earth's skies every 76 years, bright enough at times to be visible to the naked eye. When spacecraft and telescopes studied Halley in the 1982nd, they provided the first close scientific look at a comet's chemical fingerprint. Among the many elements detected in Halley's gases was once again nickel. And just as with Borisov, the amount of iron released into the gas phase was surprisingly low. The imbalance was clear. Nickel dominated the spectrum, while iron was present only in trace amounts. This finding was crucial for interpreting TR3 Atlas. If one of the most well-documented comets in our solar system showed the same pattern, then the phenomenon could not be dismissed as unique, nor as evidence of artificiality. Instead, it pointed toward a natural mechanism common to comets across different environments. The fact that both an interstellar comet like Borisov and a periodic solar system comet like Halley displayed this chemistry suggested that the explanation lay not in alien engineering, but in the fundamental differences between how nickel and iron behave under heat and radiation. By the time scientists compared TR3 Atlas with Halley and Borisov, the mystery began to shift. Rather than asking, could this be artificial? The more pressing question became, what chemistry allows nickel to escape so easily while iron remains hidden? And that question brought the focus directly onto the atomic and molecular properties of the two metals, the subtle details of their volatility, stability, and interaction with sunlight. At first glance, nickel and iron seem almost interchangeable. Both are transition metals, both are forged in the same stellar processes, and both are found together in meteorites and planetary cores. But at the atomic level, their behavior in space can be very different. The key lies in volatility, how easily an element or compound can vaporize. Nickel has the ability to form compounds such as nickel carbonyls, molecules that are unusually volatile. Under the influence of sunlight, these compounds break apart, releasing nickel atoms into space. Even at relatively low temperatures, this process can occur, making nickel easier to detect in a comet's surrounding gas. Iron, by contrast, tends to bind into highly stable minerals. These minerals do not break down easily under mild heating. To release iron into gas form, the temperatures usually have to be much higher than those typical of a comet merely approaching the sunday. As a result, iron tends to remain locked inside dust grains, invisible to spectroscopic instruments, unless the comet is heated far more intensely. This difference explains why telescopes might see bright nickel signatures but faint or absent iron lines. It is not that the iron isn't there, it is simply more reluctant to escape. The nickel is volatile, the iron is stubborn. Another factor is the sensitivity of instruments. Spectrographs detect light emitted or absorbed at specific wavelengths. Nickel's emissions, under the right conditions, can stand out more strongly than those of iron, especially if iron is present only in trace amounts. At great distances, faint signals can easily sink below the detection threshold, giving the illusion of absence. In short, nickel is chemically predisposed to reveal itself, while iron hides. What looks like an anomaly may be nothing more than a natural consequence of chemistry. This understanding reframes the puzzle of TR3 Atlas. The detection of nickel without iron does not require alien technology as an explanation. Instead, it highlights how small differences in atomic behavior can produce large effects in the observations we make across space. But does this mean the case is closed? Not entirely. The challenge is to prove that this explanation holds consistently. And for that, scientists turn to more detailed modeling and to continued observations of TR3 Atlas as it moves closer to the sunday to understand the weak iron signal in TR3 Atlas. It helps to think about how elements are locked inside cometary material. Comets are often described as dirty snowballs, mixtures of ice, dust, and rock fragments held together since the birth of their parent star system. Within this mixture, metals like iron are not free-floating. Instead, they are bound tightly inside refractory minerals, compounds that resist heat and remain solid until extremely high temperatures are reached. This is the main reason why, when a comet warms near a star, we may detect volatile gases like carbon dioxide and even nickel carbonyl compounds, but not iron gas. Iron requires much more intense heating to break free from its mineral cages. Unless the comet gets very close to the Sun, those temperatures are rarely reached. Nickel, on the other hand, has an advantage. It can form volatile complexes that disintegrate more easily under solar radiation. Even as the comet is still relatively far from the Sun, nickel can be liberated into the gas phase, where it becomes visible to spectrographs. The result, a strong nickel signature, but little to no iron. This is not a new phenomenon. Observations of Halley's comet in the 1982nd showed the same imbalance, nickel lines bright and detectable, iron weak and barely measurable. When Borisov entered our solar system, the pattern repeated. And now TR3 Atlas appears to follow the same chemistry. There is also the matter of instrument sensitivity. Even when iron gas is present, it may be released in such small amounts that our current instruments cannot distinguish its spectral lines from background noise. Nickel, being more volatile, produces a stronger, clearer signal. This is why astronomers caution against interpreting the lack of an iron detection as true absence. It may simply be that we cannot see it yet. As TR3 Atlas continues its path toward the Sun, higher temperatures may eventually free more iron, allowing it to appear in future observations. For now, the evidence suggests a natural explanation. Iron is simply harder to liberate, and our instruments are not yet sensitive enough to pick it out in the faint light of a distant, icy traveler. The next step is to consider where TR3 Atlas currently stands in its journey, and why its stage of approach to the Sun may be the deciding factor in what we can or cannot detect. At this point in its journey, TR3 Atlas is still relatively far from the Sunday. The energy it receives is enough to warm its surface and trigger the release of some volatile gases, but not enough to unleash the full chemical inventory locked deep within. This context is crucial. When the Very Large Telescope recorded the spectrum of TR3 Atlas, the instruments captured a clear and repeated signal of nickel gas. But no corresponding signal of iron was present above the detection threshold. Astronomers interpret this with caution. The absence of iron does not prove that iron is missing altogether. Instead, it suggests that under the current temperature conditions, iron remains bound in minerals too stable to break apart. Nickel, with its more volatile compounds, is easier to free even at this distance from the Sunday. The sensitivity of the instruments also plays a role. At such faint magnitudes, the line between detection and non-detection is razor thin. A trace of iron could be present, but drowned out by noise in the data. Only as TR3 Atlas grows brighter as solar heating intensifies and more material is ejected will astronomers be able to tell whether iron begins to show itself in measurable quantities. This stage of incomplete chemistry is not unusual for comets. Many show evolving spectra as they approach the Sunday. Early detections highlight volatile compounds like carbon dioxide, while heavier materials remain hidden until the comet is much closer. The fact that TR3 Atlas fits this pattern is another hint that its behavior is natural. Still, the nickel detection stands out because of how strong it is compared to the missing iron. That imbalance is what set off the wave of speculation in the first place. For astronomers, however, the case is still open. TR3 Atlas is under active observation, and its story is only beginning to unfold. As it moves inward, its temperature will rise, its tail will grow, and its spectrum will reveal more. The nickel lines may remain dominant, or iron may finally emerge from hiding. Until then, the most accurate conclusion is the cautious one. Nickel is visible now, iron is not, but that may simply be a matter of timing and sensitivity. In the next part, we will look more closely at what the VLT study itself concluded and why the scientists behind it favored natural explanations rather than anything artificial. When the Very Large Telescope team published their findings on TR3 Atlas, they were precise in their wording. The detection of gaseous nickel was confirmed, and the lack of detectable iron was noted. But nowhere in the paper did the authors suggest an artificial origin. Instead, the study emphasized natural explanations. The conclusions were clear. The unusual chemical signal was fascinating, but it did not constitute evidence of alien technology. The scientists outlined several possible reasons why nickel could be released more easily than iron. All of them relied on known chemical processes, not speculation about engineering. This distinction is important. Popular media often highlights the most sensational interpretations, but in scientific literature, the standards are stricter. Claims must be supported by repeatable evidence and grounded in established physics and chemistry. In this case, the evidence did not justify extraordinary conclusions. The study's authors pointed out that similar detections had already been made in other comets, such as Borisov and Halley. In each case, nickel appeared prominently, while iron was faint. The pattern suggested that TR3 Atlas was not unique. It was part of a broader trend in cometary chemistry. The scientists also noted that the absence of iron in the spectrum was likely due to instrument sensitivity and temperature conditions, not because iron was missing entirely. They argued that as TR3 Atlas approached the Sun, more iron might eventually be detected. Until then, the data remained incomplete, and the simplest explanation was that nickel was easier to release than iron. The tone of the paper was cautious but optimistic. Far from dismissing the finding as unimportant, the authors highlighted how it expanded our knowledge of cometary composition. TR3 Atlas, they suggested, was teaching us something new about how metals behave in icy bodies, knowledge that could reshape models of planetary formation, both in our solar system and in others. In short, the scientific conclusion was straightforward. Nickel without iron does not prove artificiality. It highlights gaps in our understanding of cometary chemistry, but those gaps can be filled with natural processes. And to reinforce this point, the authors went further, outlining 3 specific natural mechanisms that could explain the observation. In their published study, the astronomers behind the TR3 Atlas observations did not leave the mystery unresolved. They offered 3 natural mechanisms that could plausibly explain why nickel appeared in the spectrum while iron did not. 1. Nickel carbonyl compounds. Nickel is capable of forming volatile molecules, such as nickel carbonyls. These compounds are unstable when exposed to solar radiation. As sunlight strikes a comet, nickel carbonyls can break apart, liberating nickel atoms into the surrounding coma. Iron, however, does not form similar volatile compounds as easily. This makes nickel far more likely to appear in gas form at earlier stages of heating. 2. Organic complexes containing nickel. The second possibility involves organic molecules, carbon-based compounds, that bind nickel within their structures. These complexes can be fragile, breaking down under ultraviolet light and moderate heat. When they do, nickel atoms are released. Iron, again, is less likely to participate in such chemistry, remaining bound in more stable mineral forms. 3. Nickel-rich dust grains. A third explanation focuses on tiny dust particles embedded in the comet's ices. If these grains are rich in nickel, they can sublimate or fragment at relatively low temperatures, releasing nickel into the coma without requiring the extreme heat needed to liberate iron. All 3 mechanisms share one feature. They rely on astrochemistry, not engineering. The processes are natural, the kind of reactions that can occur in cold, ancient bodies formed billions of years ago in other star systems. The study emphasized that none of these explanations excluded the presence of iron in TR3 Atlas. Instead, iron might simply remain hidden bound inside refractory minerals or released only when the comet nears the Sun more closely. The absence of an ion signal, therefore, was interpreted as a limitation of current detection, not proof of absence. By presenting these natural pathways, the authors made their stance clear. There is no need to invoke artificiality when well-understood chemistry can account for the data. But if this is the case, why did the alien hypothesis continue to gain traction outside the scientific community? The answer lies in how extraordinary claims capture the imagination and in how easy it is to overlook natural precedents. At first glance, the idea that TR3 Atlas could be artificial is tempting. Nickel without iron looks unusual, and unusual results often invite unusual explanations. But when placed in context, the case for artificiality weakens quickly. The most important reason is precedent. As we have seen, Borisov and Halley's comet both showed the same imbalance, bright nickel lines in their spectra, while iron appeared faint or nearly absent. In both cases, the comets were unquestionably natural. Borisov's interstellar trajectory and Halley's centuries of periodic returns leave no room for doubt. If nickel can dominate over iron in them, then it can do the same in TR3 Atlas. The second reason lies in consistency with cometary behavior. TR3 Atlas is shedding carbon dioxide, forming a tail, and showing all the hallmarks of a volatile-rich body warmed by sunlight. An artificial spacecraft would not produce such emissions naturally. Its behavior is entirely consistent with a comet. Third, the published scientific study explicitly stated that natural explanations were sufficient. The astronomers who analyzed the data never suggested alien involvement. Their conclusions were rooted in chemistry, volatile nickel compounds, organic complexes, and dust grain sublimation. No extraordinary claim was required. Finally, the principle of scientific caution comes into play. Extraordinary claims require extraordinary evidence. A single unusual detection, especially one with possible natural explanations, does not justify leaping to the conclusion of alien technology. To do so would be premature and would risk drawing attention away from the real scientific significance of the finding. This does not mean astronomers are closed-minded. If TR3 Atlas were to consistently defy natural models, if repeated observations continue to show impossible patterns, then the discussion might change. But so far, every feature of TR3 Atlas has parallels in comets we already know. The alien hypothesis lingers mostly outside of science, in headlines, online forums, and public imagination. Inside the scientific community, the consensus remains clear. TR3 Atlas is most likely a natural object. Its odd chemistry, a puzzle for astrochemistry, not a sign of engineering. Yet, this raises another question. If the natural explanation is strong, why does iron remain so elusive in these detections? To answer that, we need to examine not just chemistry, but the limits of our instruments. When we look at TR3 Atlas through our most advanced telescopes, we are not seeing the object directly in fine detail. Instead, we are collecting faint streams of photons, stretched across millions of kilometers of space, blurred by dust, and dispersed into spectral lines that must then be interpreted. Every data point comes with uncertainties. The Very Large Telescope, VLT, is one of the most powerful optical facilities in the world, yet even it has sensitivity limits. When astronomers detect nickel in TR3 Atlas, they are seeing spectral lines that rise clearly above the noise threshold. But when they look for iron, The lines may simply be too weak to distinguish from background fluctuations. This does not mean iron is absent. It means it is below detection limits at this stage of observation. The faintness of the object, combined with its current distance from the Sun, means that any iron being released is likely at levels too low to measure with confidence. The same issue has arisen before. In Borisov and Halley, iron signals were detected only faintly, despite nickel showing strongly. Even then, the detections required careful analysis and sometimes multiple instruments. If such difficulty exists for nearby and bright comets, it is no surprise that a distant interstellar traveler, like TR3 Atlas, poses an even greater challenge. Instrument sensitivity is only part of the story. The timing of observation also matters. TR3 Atlas is still relatively early in its approach to the Sunday. At these distances, surface heating is moderate. Nickel, with its more volatile compounds, can escape into the coma. Iron, bound into refractory minerals, remains locked inside. Only as the comet nears the Sun and temperatures rise significantly might those minerals begin to release iron gas at levels we can measure. This is why astronomers insist that ongoing monitoring is essential. A single observation provides only a snapshot. To understand TR3 Atlas fully, scientists need to track it continuously, watching how its spectrum evolves as it gets closer to the Sunday. If iron emerges later, the imbalance will make sense. If it never appears, then the mystery deepens. But either way, only long-term observation can answer the question. In short, the limits of our instruments remind us to be careful. What looks like absence may simply be invisibility. The cosmos often hides its details at the very edge of our detection. And this, in turn, highlights a broader lesson. Science requires patience. The story of TR3 Atlas is not finished, and only time and careful study will reveal the truth. When faced with a mystery like TR3 Atlas, it is tempting to want answers immediately. The detection of nickel without iron feels urgent, as though it must be explained right now. But science does not work at that pace. It works through steady accumulation of data, cautious interpretation, and careful testing of hypotheses. In astronomy especially, patience is not optional, it is a requirement. Objects like TR3 Atlas move slowly on cosmic timescales. Their behavior changes gradually as they travel toward or away from the Sunday. Each stage reveals new information. To leap to conclusions based on one moment of observation would risk misunderstanding the entire story. History provides many reminders of this. When Oumuamua passed through the solar system in 2017, its unusual shape and lack of a visible tail triggered headlines about alien spacecraft. But follow-up studies showed that natural explanations from hydrogen outgassing to unusual geometry were sufficient. The first impressions were dramatic, but they were not the final word. The same is true for TR3 Atlas. Right now, the data show nickel, but not iron. Later, as the object heats further, iron may emerge. Or perhaps it will remain hidden, forcing scientists to refine their chemical models. Either outcome will provide answers, but only if we wait for more evidence. This patience is not hesitation. It is discipline. Science advances not by feeding our immediate curiosity, but by resisting it when the data are incomplete. Each observation is a piece of a larger puzzle. Only when enough pieces are in place can we see the full picture. For the public, this can feel unsatisfying. Headlines promise instant solutions, dramatic revelations, or alien encounters. But astronomers must resist that pressure. Their responsibility is not to entertain, but to explain, and to do so with integrity. TR3 Atlas reminds us that science is not about quick conclusions. It is about watching, waiting, and allowing nature to reveal itself on its own timescale. And yet, even with this cautious approach, the idea of alien technology remains powerful. Many people continue to hope that TR3 Atlas is more than a comet. Why does that idea persist so strongly, even when the evidence points elsewhere? Why is it that every time an unusual object enters our solar system, the first thought in many minds is, what if it's a spacecraft? The answer lies in our deep-rooted curiosity. For centuries, humanity has looked to the skies with wonder, asking if we are alone. Every strange signal, every anomaly, becomes a canvas onto which we project that question. TR3 Atlas, with its puzzling chemistry, is only the latest case to ignite that hope. The detection of nickel without iron feels unusual, and unusual often gets equated with unnatural. From there, the leap to alien technology is short, especially in an age when news travels instantly across social media. Headlines that suggest artificiality spread quickly, capturing imaginations and sparking debate far beyond the scientific community. But the temptation goes deeper. Discovering evidence of extraterrestrial intelligence would be one of the most profound moments in human history. It would confirm that life, and perhaps civilization, is not unique to Earth. For many, the longing for that discovery makes every anomaly feel like a potential breakthrough. Astronomers are not immune to that excitement. They too would be thrilled to find proof of alien technology. But they are bound by evidence. They know that extraordinary claims require extraordinary proof, and that leaping too quickly risks damaging credibility. That is why, when faced with TR3 Atlas, scientists emphasize caution. Yes, nickel is there. Yes, iron is not. But this alone is not evidence of engineering. Natural explanations are far more likely, supported by precedents in Borisov and Halley. Still, the alien hypothesis lingers in the background, fueled by human imagination and the history of past debates. From the canals once imagined on Mars to the search for signals in radio astronomy, humanity has often mistaken anomalies for signs of intelligence only to later find natural causes. TR3 Atlas fits this pattern. For now, it is best explained as a comet with unusual chemistry. But the hope of something more remains, not because of the data, but because of what we want the universe to contain. Next, we will turn to one scientist in particular whose name often appears in these discussions, Avi Loeb, and why he argues that considering alien possibilities should remain on the table, even if the evidence is thin. Whenever an unusual astronomical discovery makes headlines, one name often appears in the discussion. Avi Loeb, a Harvard astrophysicist known for his willingness to consider bold possibilities. Loeb became widely known after the discovery of Oumuamua in 2017. While most scientists lean toward natural explanations for the object's strange shape and motion, Loeb argued that it might be an alien probe or a fragment of alien technology. His willingness to state that openly drew both criticism and admiration. To some, it was speculative to the point of recklessness. To others, it was a refreshing reminder that science should not close itself off to extraordinary possibilities. In the case of TR3 Atlas, Loeb and others like him are not directly claiming that the object is artificial, but the same spirit of speculation surrounds it. The unusual nickel detection, without iron, makes it a candidate for discussion. To those in favor of keeping the alien hypothesis alive, the point is not that TR3 Atlas is engineered, but that it is worth asking whether it could be. This raises a broader issue in science. How much room should there be for speculation? On one hand, unchecked speculation can mislead the public and damage scientific credibility. On the other, refusing to ask bold questions can prevent us from seeing possibilities that later turn out to be true. Most astronomers walk a careful line. They recognize the importance of open-mindedness, but they stress that conclusions must be based on evidence. In the case of TR3 Atlas, the evidence strongly favors natural explanations, especially when placed in context with Borisov and Halley. Still, the alien hypothesis remains in the background, partly because of figures like Loeb, who argue that considering all possibilities, however unlikely, is a healthy part of scientific debate. For the public, this dynamic can be confusing. Headlines focus on speculation, while the actual research emphasizes caution. But in truth, both play a role. The cautious approach builds reliable knowledge. The speculative approach keeps imagination alive and reminds us that the universe may still surprise us. In the end, TR3 Atlas shows us both sides of this balance: the discipline of science on one side and the temptation of speculation on the other. And both are needed, one to anchor us to evidence, the other to ensure we never stop asking daring questions. Next, we will see why comparisons with known comets are so essential in science and how they help astronomers avoid misleading conclusions about objects like TR3 Atlas. When astronomers are confronted with something unusual, one of the first steps is to ask, have we seen anything like this before? In science, context is everything. Without it, an anomaly can look like evidence of something extraordinary. With it, the same anomaly often becomes part of a larger, natural pattern. That is why the comparison of TR3 Atlas with comets like Borisov and Halley has been so important. Both of those objects showed the same imbalance between nickel and iron, even though they came from very different origins, one interstellar, one within our solar system. If nickel without iron were unique to TR3 Atlas, it might raise stronger doubts. But because it has been seen elsewhere, the balance of probability shifts decisively toward a natural explanation. These comparisons also remind us that comets are not uniform objects. Each one carries the chemical imprint of its birth environment. Some are rich in water ice, others in carbon monoxide or carbon dioxide. Their compositions vary depending on where in their parent systems they formed and how much they have been altered by past encounters with stars. TR3 Atlas, then, may simply represent a comet from a region of space where nickel is bound in compounds that release more easily than iron. It is not proof of engineering, but proof of diversity in cometary chemistry. Comparisons also protect science against bias. Without them, it would be easy to interpret nickel without iron as a singular, artificial signature. With them, the anomaly becomes a trend that demands a chemical explanation rather than a technological one. This method, anchoring unusual data against established precedents, is one of the most powerful tools in science. It prevents extraordinary claims from standing alone and forces new observations to fit within the broader framework of what is already known. And as TR3 Atlas continues its approach toward the Sun, comparisons with past comets will remain vital. If its behavior continues to match that of natural bodies, the case for artificiality weakens further. If it diverges significantly, then astronomers will know they are dealing with something new. Either way, science advances not by isolating mysteries, but by connecting them. TR3 Atlas is not just a lone puzzle in the night sky. It is part of a larger story about the chemistry and diversity of comets across the universe. Next, we will look ahead at what scientists expect as TR3 Atlas moves closer to the Sun, and why future observations may be decisive in solving the nickel-iron mystery. TR3 Atlas is still on its way inward, pulled steadily closer to the Sun by gravity. With each passing week, the amount of energy it receives increases. This warming will trigger deeper layers of its ices to sublimate, releasing new materials into space. For astronomers, this stage is critical. because it may reveal whether the mystery of nickel without iron is a temporary illusion or a true chemical imbalance. As the temperature rises, refractory minerals that hold iron will begin to break down. If iron gas exists in Atlas, it should eventually appear in the spectrum once conditions are hot enough. Detecting it will not be easy. The signals may still be faint, but as the comet brightens, the chances of spotting iron improve significantly. If future observations show iron emissions alongside nickel, the anomaly will be resolved. Atlas will fall into the same category as Borisov and Halley, both of which eventually revealed faint traces of iron under closer study. The imbalance will remain interesting, but no longer mysterious. If, however, Atlas continues to release nickel without any measurable iron, even under higher temperatures, the case becomes more puzzling. Such persistence would force astronomers to revisit their chemical models and ask whether there are conditions that could suppress iron release indefinitely. It would not prove artificiality, but it would suggest an unusual pathway of comet formation or an environment very different from what we have seen before. Either outcome will advance science. If iron is found, we confirm that comets follow a broader chemical pattern, reinforcing current models. If iron is not found, we discover that nature can produce comets with compositions stranger than expected, opening new questions about how and where such bodies form. That is why telescopes around the world, and even in space, continue to monitor Atlas closely. Every new measurement adds a piece to the puzzle. Each data set refines the models that will eventually give us a clearer answer. The comet's path toward the Sun is not just a journey through space, it is a journey toward greater understanding. And for scientists, patience now will pay off later, when Atlas reveals more of itself under the relentless heat of our star. Next, we will consider what might happen if Atlas truly fails to show iron at any stage, and why that scenario, while unlikely, would represent an intriguing surprise. What if TR3 Atlas never shows iron? What if, even as it sweeps closer to the Sun and heats to temperatures that normally liberate refractory minerals, iron continues to remain hidden? This is the scenario that keeps the mystery alive. If nickel continues to dominate the spectrum while iron remains absent, it would challenge existing models of cometary chemistry. Astronomers would have to ask whether TR3 Atlas formed in an environment where iron was depleted or whether its internal structure somehow prevents iron from escaping. Such a result would not automatically imply an artificial origin. Instead, it would suggest that nature is more diverse than expected. Comets are already known to be varied in composition, some rich in water ice, others dominated by carbon monoxide or methane. TR3 Atlas might represent an extreme case, a body with nickel-bearing compounds unusually prone to release, while iron stays locked away. It is also possible that the conditions under which Atlas formed were chemically unique. Perhaps in its home system, iron became trapped in minerals that resist sublimation far more strongly than those found in our solar system. If so, Atlas would carry a signature not of alien engineering, but of an alien birthplace, a natural record of how different stellar nurseries shape the building blocks of planets. For astronomers, such a discovery would be just as exciting as detecting iron. It would expand the catalogue of cometary types and challenge theories of planetary formation. It would also provide new insights into how heavy elements behave in cold, distant regions of space. The persistence of nickel without iron would be a surprise, but in science, surprises are opportunities. They are the moments when old models must be re-examined, when assumptions are tested, and when new knowledge emerges. So even if TR3 Atlas defies expectations, the lesson will be the same. Nature writes its own rules, and our task is to understand them. Next, we will step back from the nickel-iron debate, and look at the broader value of TR3 Atlas, what it is teaching us about comets, chemistry, and the diversity of planetary systems across the galaxy. While the debate over nickel and iron dominates discussions about TR3 Atlas, the object's true importance extends far beyond this single chemical detail. Every interstellar visitor provides scientists with something rare, a direct sample of material forged in another star system. Most of what we study in astronomy comes from within the solar system. Asteroids, comets, and planets all share a common origin formed from the same protoplanetary disk billions of years ago. Interstellar objects like TR3 Atlas, however, are different. They were born elsewhere, shaped by different stars, environments, and histories. They carry with them the unique chemical fingerprints of their home systems. This makes TR3 Atlas invaluable. By studying it, astronomers are not just learning about one comet, they are learning about how matter behaves across the galaxy. If Atlas shows an unusual nickel-to-iron balance, that could reflect conditions in its parent system, perhaps a star-forming region with distinct chemistry, or a planetary nursery, where iron became locked into stable minerals while nickel remained more available. Even beyond the nickel question, Atlas's emissions of carbon dioxide are noteworthy. The high levels detected suggest that it contains ices in unusual proportions compared to typical solar system comets. This, too, points to differences in how comets form in different environments. Each measurement adds to a growing library of knowledge about interstellar bodies. With just 3 confirmed examples so far, Oumuamua, Borisov, and Atlas, the sample size is small, but the implications are enormous. Each one reveals that the galaxy is chemically diverse, that planetary systems can produce objects unlike those we are familiar with, and that our solar system is not a perfect template for the rest of the universe. The broader lesson is simple but profound. TR3 Atlas is not just a mystery to be solved, it is a messenger from another world. Whether or not its chemistry perfectly matches our expectations, its very existence enriches our understanding of how planets, comets, and star systems evolve. In the next part, we will explore why discoveries like this matter for the long-term goals of astronomy, and why studying a single interstellar comet can change our perspective on the galaxy as a whole. At first, the nickel-iron puzzle of TR3 Atlas may seem like a narrow chemical detail, the kind of subtle distinction that only specialists would care about. But in astronomy, small details often open the door to big ideas. Studying interstellar comets like Atlas gives us a direct glimpse into the building blocks of other planetary systems. Just as meteorites on Earth carry the history of our solar system's formation, comets from beyond the Sun carry clues about worlds we may never see directly. Each one is a fragment of a distant nursery of stars and planets, preserved for billions of years and delivered to us by chance. That is why every observation counts. The detection of nickel without iron, whether ultimately explained by chemistry or not, forces scientists to refine their models of how elements are distributed in comets. The unusually high levels of carbon dioxide push us to ask how ices vary between star systems. Even the brightness fluctuations in Atlas's coma raise questions about its internal structure. In the long term, this knowledge has enormous implications. By studying objects like Atlas, astronomers can begin to answer broader questions. Do all star systems produce comets, or only some? How do the ratios of metals and ices vary between different stellar environments? Can interstellar comets deliver chemical ingredients for life across the galaxy, just as comets may have done on Earth? Every interstellar visitor we detect is a chance to test these questions against reality. With only a handful discovered so far, each one is precious. TR3 Atlas is not just another comet. It is part of a new frontier in astronomy, where the galaxy itself becomes our laboratory. And this is why the object has drawn so much attention, even beyond the speculation. Whether or not it turns out to be unusual in the end, its study advances the long-term goal of astronomy: to understand our place in the cosmos by comparing ourselves with worlds far beyond the Sunday. Next, we will look at the public fascination with aliens and why, even when the evidence points to natural explanations, extraordinary ideas continue to capture the imagination. Whenever an unusual discovery makes headlines in astronomy, one explanation tends to dominate popular imagination: aliens. The reasons go beyond curiosity. The idea of extraterrestrial intelligence speaks directly to our deepest hopes and fears. If alien civilizations exist, then humanity is not alone. Our story would be just one among countless others across the galaxy. For many, that possibility is profoundly exciting, even comforting. For others, it is unsettling, raising questions about what such civilizations might mean for us. This emotional weight is why anomalies like TR3 Atlas capture attention so quickly. A comet that shows nickel without iron is, to scientists, a puzzle in astrochemistry. But to the public, it becomes a candidate for alien engineering. The difference lies in how each group interprets the unknown. Scientists default to natural mechanisms, while the public is often drawn to extraordinary ones. History has shown this pattern repeatedly. In the late 19th century, astronomer Giovanni Schiaparelli mapped what he thought were canals on Mars. The public interpreted them as artificial structures, the work of an advanced Martian civilization. Later, more accurate telescopes revealed they were optical illusions. In 1967, the discovery of the first pulsar produced signals so regular that the detection team nicknamed it LGM, Little Green Men. It turned out to be a rapidly rotating neutron star. TR3 Atlas fits neatly into this tradition. Its chemical anomaly is real, but the leap to aliens is premature. Scientists point to chemistry, while speculation turns to engineering. The fascination persists not because the evidence is strong, but because the idea of aliens is irresistible. And this fascination is amplified in the modern world, where news spreads instantly through headlines and social media. A phrase like "possible alien probe" travels far faster than "nickel chemistry in cometary coma." The former excites, the latter explains. This tension between scientific caution and public imagination is not necessarily harmful. It reflects two sides of human curiosity: the disciplined search for truth and the boundless hunger for wonder. But it does place a responsibility on scientists and communicators to bridge the gap, to honor the excitement without overstating the evidence. Next, we will turn to this responsibility more closely: the integrity of science communication and why honesty matters when explaining discoveries like TR3 Atlas. The story of TR3 Atlas is not just about chemistry in space. It is also about how science is communicated. When a discovery is first reported, scientists often use careful technical language. They describe uncertainties, outline possible explanations, and avoid dramatic claims without evidence. But once that discovery leaves the pages of a research paper and enters the news cycle, the tone can change dramatically. Headlines often highlight the most sensational angle. A phrase like "nickel detected without iron" becomes evidence of alien engineering. The cautious language of probabilities and uncertainties gets replaced by absolutes and speculation. By the time the story reaches the public, the scientific nuance is often lost. This is why integrity in communication is so important. Scientists and communicators alike have a responsibility not to exaggerate findings for attention. The temptation to do so is real. Bold claims attract viewers, generate clicks, and spread quickly on social media. But if the claims are not supported by evidence, the excitement collapses when the truth emerges. Trust in science erodes, replaced by cynicism. With TR-3 Atlas, the responsible approach is to present the facts as they are. Nickel has been detected, iron has not. Similar patterns were seen in Borisov and Halley. Natural explanations exist, and they are sufficient. That is the story the data supports. To frame it as proof of alien technology would not just be misleading, it would risk undermining the credibility of astronomy as a whole. At the same time, communicators must balance integrity with accessibility. A purely technical explanation may fail to capture public attention. The challenge is to tell the story in a way that is both engaging and accurate, to share the wonder without distorting the science. Astronomy thrives on this balance. It is a field built on awe and discovery, but also on rigor and evidence. When both are preserved, the public can share in the wonder of discoveries like TR-3 Atlas without being misled. And in the case of Atlas, there is no shortage of wonder to share. Even without aliens, the nickel-iron puzzle teaches us something new about comets and the chemistry of planetary systems. That knowledge is valuable on its own, and it will only grow as Atlas continues its journey toward the Sunday. Next, we will look at the lessons this study offers for science itself. How TR-3 Atlas is reshaping our understanding of cometary chemistry and the diversity of interstellar visitors. The case of TR-3 Atlas demonstrates how even a single observation can reshape our scientific understanding. What at first appeared to be a puzzling anomaly, nickel detected without iron, has instead become a valuable clue about the hidden chemistry of comets. The key lesson is that cometary compositions are more complex than once thought. For decades, comets were seen primarily as mixtures of ice and dust, relatively simple remnants of planetary formation. But as instruments have become more sensitive, subtle differences in elemental chemistry have come into focus. Atlas, like Borisov and Halley before it, reveals that heavy metals, such as nickel, can behave differently from their chemical siblings, like iron. This has direct consequences for astrochemistry. It forces scientists to refine their models of how metals are distributed within icy bodies, how they bond into compounds, and how they are released under solar heating. It also underscores the importance of volatility differences, the fact that even elements formed side by side in a supernova can diverge in their behavior billions of years later. Beyond chemistry, Atlas highlights the value of studying interstellar visitors. Every comet from another system offers a natural experiment. By comparing them with our own solar system's comets, astronomers can identify both universal patterns and unique deviations. If nickel dominance proves common across multiple comets, it may point to a fundamental rule of chemistry in cold space. If it remains rare, Atlas may represent a distinctive fingerprint of its home system. The study also reinforces the importance of continued monitoring. A single snapshot cannot tell the whole story. Only by following Atlas through its journey, watching how its emissions evolve as it heats, can scientists confirm or challenge their interpretations. Finally, Atlas provides a lesson in humility. What began as speculation about alien technology has turned into a reminder that nature is often stranger, subtler, and more inventive than we imagine. The absence of iron is not evidence of engineering, it is evidence of how much we still have to learn about the chemistry of small bodies in space. In this sense, TR-3 Atlas is not just another cometary visitor. It is a teacher, reminding us that even familiar elements can surprise us when observed under new conditions. Next, we will follow Atlas further on its path, considering what its continuing journey toward the Sun may reveal and why the months ahead are crucial for solving its mysteries. As TR3 Atlas continues its trajectory through the solar system, astronomers remain watchful. Each passing week brings the object closer to the Sun, and with that, new opportunities for observation. The warmth of solar radiation will dig deeper into its icy layers, releasing fresh material and possibly exposing the hidden chemistry within. For scientists, the key question remains, will iron finally appear? If so, it will confirm that Atlas behaves just like other comets, with nickel released early and iron delayed until higher temperatures break down its minerals. This would neatly resolve the puzzle, placing Atlas alongside Borisov and Halley as part of a broader, natural pattern. If, however, Atlas continues to emit nickel without detectable iron, even at closer range, then the mystery will deepen. Such persistence would suggest that Atlas either formed in an environment fundamentally different from ours, or that its structure is unusual in ways not yet understood. In that case, astronomers will need to revisit their models of cometary chemistry, exploring possibilities not yet considered. But either way, the journey is valuable. Every spectrum recorded, every change in brightness, and every new feature in its tail adds to our knowledge of interstellar visitors. These objects are fleeting, most pass through once and are never seen again. The chance to study them is rare, and TR3 Atlas offers a window into a part of the galaxy we could otherwise never reach. The months ahead will be decisive. As Atlas heats further, the balance of gases may shift, revealing hidden elements or confirming its unusual profile. New instruments, such as the James Webb Space Telescope, may provide data at wavelengths inaccessible to ground-based telescopes, offering sharper insight into its chemistry. Whatever the outcome, TR3 Atlas has already earned its place in astronomy. It has challenged assumptions, tested instruments, and reminded us that the universe is full of surprises waiting to be uncovered. And so, astronomers will continue to track its progress, collecting every photon they can, waiting to see whether this strange visitor reveals iron at last, or whether it departs the solar system, leaving behind a mystery still unsolved. Next, we will close our exploration by looking at the open question left for the future. What TR3 Atlas ultimately represents in humanity's search to understand the universe. TR3 Atlas is, at its core, a reminder of how little we truly know about the universe. It may be a comet behaving within the bounds of chemistry, or it may turn out to possess features that push our models into unfamiliar territory. Either way, it represents something rare, a messenger from beyond our solar system carrying with it the secrets of a distant birthplace. For now, the puzzle remains unresolved. Nickel shines clearly in its spectrum. Iron does not. Natural explanations exist: volatile nickel compounds, organic complexes, or stable iron minerals resisting release. And yet, the absence of iron is still striking enough to keep astronomers watching, waiting for the next chapter. The real significance lies not in whether Atlas is artificial or natural, but in what it teaches us about the diversity of matter across the galaxy. Each interstellar object expands our vision, showing us that the solar system is not a template for everything else. Other worlds form differently, their comets carrying new combinations of metals and ices, shaped by stars unlike our own. Still, the question lingers: what if Atlas never reveals iron? What if its chemistry defies every natural model we have? Would we be ready to consider possibilities we now dismiss? Or would we simply refine our theories once again, discovering a new layer of nature's complexity? This is the balance between science and imagination. Science demands evidence, caution, and patience. Imagination asks us to keep our minds open to the extraordinary. TR3 Atlas sits at the intersection of both, a small, faint object whose light forces us to think bigger than our own world. And so the story continues. As Atlas approaches the sun, we wait to see whether its mysteries dissolve in the heat of natural explanation or whether they grow deeper, leaving us with more questions than answers. In the end, perhaps that is the real gift of TR3 Atlas. Not certainty, but wonder.